Hey everybody, this is the solution for the reading quiz on June 8th. Alright, so problem 1. We have a steel cable with a breaking strength of 20,000 newtons, or 20 kilonewtons. Okay. And we want to use this cable to tow a 8,000 kilogram object, or 8 metric ton object, across a surface with a coefficient of friction, kinetic coefficient of friction of 0.150. So mu sub k equals 0.150. So let's work this out. Let's think about this before we do any math. So the breaking strength represents the maximum amount of force that can be applied to the object, whatever it is. It weighs 8 metric tons, so it's probably something pretty big. So we can't put more than 20,000 newtons of tension in the steel cable. So let's sketch this. Here's whatever our object is. Here's the force of kinetic friction opposing its motion. And here's our steel cable, and it has some tension in it. And so let's write down Newton's second law. So there's the sum of the forces acting on our on the object. So we can't have more than, if we want to find the maximum acceleration, then we know that the tension has to be 20,000 newtons. If we go over this, it'll break. So we want to find, if we assume that the maximum amount of force that we can apply is 20,000 newtons, then we want to find exactly what the acceleration is if we put that force onto the strength, or onto the steel cable. All right, so then the force of friction, we know this force of kinetic friction is mu sub k. Let's stick a negative sign in there. Mu sub k Fn, where n is the normal force. And we know the normal force, since we're not on a slope, is just going to be mg. So we have negative mu sub k mg as our force of friction. So let's see, let's write this down. Ma equals the tension force minus mu sub k mg. And we want to find A. So we divide through by mass. So we have tension divided by mass. And then we have mu sub k times the acceleration of gravity. So that represents the maximum acceleration we can give this 8 metric ton object before that steel cable will snap and bad things will happen. So let's see, we know our tension is going to be 20,000 newtons. You know the mass of the thing is 8.00 times 10 to the third kilograms, so 8,000 kilograms. And then we have our coefficient of friction of 1.50 and the acceleration of gravity of 9.81 meters per second squared. So when we plug all those numbers in, we get an acceleration of 1.03 meters per second squared. So we cannot accelerate this object, whatever it is, faster than that, or the steel cable will break and really bad things can happen when steel cables snap under that much tension. So that's number 1. Okay, problem number 2, or 2A, I guess. We'll call this 2A. 70 kilogram box. Sketch this out. 70 kilograms. Is pulled by a 400 Newton force at an angle of 30 degrees above the horizontal. So here's our horizontal. Here's our 400 Newton force. Call that F applied. Note the decimal point after the 400 implies that it's 3 sig figs, not just 1. And we have an angle of 30 degrees, and we'll call that angle theta. And then we have some friction force acting opposite, and our coefficient of kinetic friction is 0.500, or 0.50, whatever. Okay, anyway, we want to find the friction force acting on the box in newtons. So in order to find the friction force, we need to first find the normal force. Remember, friction force is just mu sub k F n. But because our applied force is at an angle, there is a non-zero y component, and that's actually going to affect the value of the normal force. In this case, the normal force is not just going to be mg. So let's work out what the normal force is going to be using Newton's second law. So Newton's second law in the y direction. F net y, let's write down the sources of force. We have our gravitational force, which is just the weight of the box. We have our normal force. And we have the y component of the applied force. And I'll write down expressions for each of these, except normal force. Now, what is this equal to? Well, we know that the box isn't falling through the ground or being lifted up off the ground, so necessarily the net force in y still has to be 0. So let's write down expressions for these. We have negative mg for the force of gravity. We have whatever our normal force is. And we have our applied force, the y component of it. And that is going to be F applied times the sine of theta. And that's all equal to 0. So now what we need to do is solve this for the normal force. So solving it for the normal force should be pretty straightforward. And we should find that the normal force is actually just going to be mg minus the y component of the applied force. So what's going to happen is that because we're pulling up on the on this rope or whatever we're using to pull this box, it's actually going to reduce the normal force a little bit. The ground doesn't have to push up quite as hard on the box. It'll reduce the normal force, and so it'll actually, in turn, reduce the friction force a little bit. So now that we have an expression for the normal force, we can work out what the friction force is. So F sub k, again, is mu sub k times the normal force. And so we have mu sub k times mg minus F applied sine theta. So to substitute things in here to calculate that friction force. So we'll have 0.5 as our coefficient of friction. I'll use square brackets so you can see the nesting of the parentheses, but we have our 70 kilogram box times our 9.81 meters per second squared. Then we have our 400 Newton applied force times the sine of 30 degrees. And all that inside those square brackets. So when we do that product and subtraction out fully, oops, typo on my calculator. It's another typo on my calculator, sorry. We ultimately get a friction force of 243.35 newtons, and since we only have 3 sig figs, we'll truncate that to 243 newtons. Now, some of you had a negative sign on this. That's fine. I have it listed as 243. It's a little vague what the sign on the friction force is because I'm not really asking for direction or anything. I had 243 as the correct answer. If you had negative 243, it originally got marked wrong. I went through and made sure that you got credit for that because you followed the procedure correctly. You just had a sign difference. Okay, so that's it for 2A. For 2B, we want to work out, put this to the side, move my mouse out of the way. For some reason, the screen got darker. I don't know why. I have a crappy camera. Anyway, for 2B, we want to find the acceleration of the box. Specifically, we're finding the acceleration in the x direction because we've already established that ay is 0. The box isn't moving up or down. We just want to find a sub x. So that's, again, Newton's second law. So Newton's second law for the box in the x direction is going to be F net x equals, let's see, we have the x component of our applied force. And then we have the friction force. And I'm adding a negative sign to that because it's opposing the applied force. And that's going to give us ma sub x. Okay, so we know F applied x is going to be F applied times the cosine of theta. And we've already found an expression. We already have a number for f sub k, so we'll just leave that as f sub k, and that'll give us max. So now we just need to solve for a sub x. And that's going to be f applied cos theta. Oops, well, let's see if that is theta. Minus f sub k over the mass of the box. So let's see, we have our 400 Newton applied force times the cosine of 30 degrees. Minus what we calculated for the friction force, which was 243 newtons. And we divide that by the mass of the box, 70 kilograms. And when I put all that into my calculator, I calculate an acceleration of 1.48 meters per second squared. I think I have 1.47 meters per second squared on the test. That 1.48 is within the margin of error, and I think it comes from rounding the friction force to 243 instead of 243.35 when putting that in here. Anyway, that's the solution to question 2A and 2B on the quiz from the 8th. All right, question 3. Question 3A is actually a little bit tricky. You have to think a little bit about what you're doing here, because we're on an inclined plane, and that always tends to screw people up. So here's our inclined plane. It is inclined at a 30-degree angle, and we have an 8-kilogram box released on it, and it slides down the ramp. So here's our 8-kilogram box, and we know that its parallel acceleration is 0.3 meters per second squared. And we want to find the force of friction. So let's draw some arrows representing the various forces. I'm actually going to redraw this because I don't have the room to draw the arrows properly. So there's our ramp, there's the box. Let's draw some arrows. Here's our parallel force of gravity, pulling it down the ramp. Here's the force of friction. This confused a couple people. Remember, friction acts to oppose motion. If it's sliding down the ramp, then the force of friction is going to be acting in the opposite direction, and it's actually going to be acting up the ramp. So there's our force of friction. Then we have our perpendicular force of gravity and our normal force. And again, we can kind of neglect those because, as far as we can tell, the box isn't flying away from the ramp and it's not sinking through the ramp, so there's the net force in the perpendicular direction is 0. So F net sub perp. This is a symbol for indicating perpendicular, and the two parallel lines indicates parallel. I don't think I've said that before, so just so you know. So that means all we're really interested in is the forces acting in the parallel direction. So let's write down Newton's second law for the parallel forces. We know that F parallel net is equal to, let's see, the parallel force of gravity plus the force of friction. And that's equal to the mass of the box times its acceleration down the ramp. Just as a quick note, on conventions, I usually take gravity to be in the negative direction. So down the ramp in this case is going to be in the negative direction. That means that our acceleration is actually negative 0.3 meters per second squared. And that means friction in this case is actually positive. Okay, with that in mind, we know we have our expression for the parallel force of gravity. We know that is minus mg sine theta. And then we have our force of friction, and then we have ma parallel. So all we really need to do here is solve for the force of friction, F sub k, in terms of all these other things. And so in that case, we're going to have ma parallel plus mg sine theta. And when we plug numbers in, let's see, we have 8 kilogram box. We have a negative 0.3 meters per second squared acceleration plus 8 kilograms times 9.81. I'm running out of space again. And I'll just throw sine 30 in there, kind of cramped at the end. Sorry. So that's sine 30. Sorry. So when we do out all that math, we should obtain a friction force of 36.8 newtons. That looked more like a 3. I don't know if I succeeded. 36.8 newtons. So that's part A of question 3. That is the force of friction acting up the ramp, actually. I'll move that to the side. And I just drew with marker on my arm. Okay, now for question 3b, we just want to find the coefficient of kinetic friction between the box and the ramp. So let's write down what coefficient of friction is. We know that the force of friction is mu sub k times the normal force. So here we actually have to keep in mind what the normal force is. We said in the previous part of the problem, because F net perpendicular is 0, we don't need to know the normal force for the purposes of just calculating the friction force here, and that's true. But now, to calculate the coefficient of friction, we do need to know the normal force. So let's take another look at this again. We know that on a inclined plane, the perpendicular force of gravity is negative mg cos theta. And we know that the net perpendicular forces, which is normal force plus the perpendicular force of gravity, is 0. So that means that the normal force has to be the negative of the perpendicular force of gravity, or just mg cosine theta. I think I've said that before, but we'll be saying it again here. So with all that in mind, we can rewrite this equation as F sub k equals mu sub k mg cosine theta, and we can solve for mu sub k. So solving for mu sub k gives us the friction force divided by the mass times the acceleration of gravity times the cosine of the angle of inclination. And plugging numbers in, we get, let's see, we had 36.8 as our friction force. We have 9.81 meters, I have that out of order, whatever. Meters per second squared. We have our mass of 8 kilograms. Multiplication is commutative, so it doesn't matter what order I multiply them in. And then we have our cosine of 30 degrees. So if we plug those numbers into my calculator, I get a coefficient of friction of 0.541. I think I have 0.542 on the quiz. That's well within the margin of error I allow on the quiz. I imagine the 0.542 came because I didn't round 36.8 before the or when I did this calculation. All right, so that's it for the solutions to the quiz from June 8th.